I'm Eric Neyman, and this is joint work with Tim Roughgarden on a connection that we found between the problems of forecast aggregation and forecast elicitation. I'll start by telling you about these two problems, and then I will give you our main definition, which we called quasi-arithmetic pooling, that connected these two problems. Then I will give you a few reasons to believe that this notion is pretty fundamental. I'll start by talking about forecast aggregation. Let's say that you're a meteorologist and there's a hurricane approaching Florida. Now, the governor of Florida calls you up and wants to know the probability that the hurricane will directly impact Miami. So you consult three different weather models. One tells you there's a 10% chance, another says 25%, and a third says 70%. How do you combine these into one number? That is the problem of forecast aggregation, or forecast pooling, as it's sometimes called. Now, the simplest thing that you might think to do is just take the average of these numbers, and this is called linear pooling. Another common method is to convert these probabilities into odds. So, for example, 10% becomes 1 to 9. To take the geometric mean of those odds and convert those back into a probability. This is called logarithmic pooling, and while it shouldn't be obvious to you why this is natural, it really is. It has a neat interpretation in terms of averaging the expert's Bayesian evidence, and empirically it does quite well, often better than linear pooling. These are the two most well-studied pooling methods, and I'd just like to note that they work just as well for probability distributions over more than just two outcomes. The second problem is forecast elicitation. This is the question of how do you truthfully elicit a probabilistic forecast from an expert? And the answer is that you use a proper scoring rule. So a scoring rule is a contract that specifies how much an elicitor pays to the expert as a function of the probability distribution P that the expert reports and the eventual outcome J. And a scoring rule is called proper if the forecaster is incentivized to tell the truth, meaning that they maximize their expected score by reporting their true belief. By far, the two most commonly used proper scoring rules are the quadratic and logarithmic scores. I won't go into why these are proper, but I have written their formulas on this slide. Now, our contribution relates these two problems of aggregation and elicitation. And if you want to pay attention to one slide during this talk, let it be this one. The key takeaway is that there is a tight connection between forecast aggregation and forecast elicitation. And this connection is mediated via a notion of pooling with respect to a scoring rule. So that means you give me a proper scoring rule, and I will give you back a forecast aggregation method. And we call this quasi-arithmetic pooling with respect to the scoring rule, or QA pooling for short. What's so special about QA pooling? Well, one thing is that it maps the quadratic scoring rule to linear pooling and the logarithmic scoring rule to logarithmic pooling, which means that it maps the two most commonly used proper scoring rules to the two most well-studied opinion pooling methods. Additionally, it is optimal in two different senses that I will tell you about. And the class of all QA pooling methods is characterized by a neat list of axioms. I really want to tell you about this definition, but first I want to motivate it by discussing how to choose a proper scoring rule. There are infinitely many proper scoring rules, so how do you choose which one to use? And let's zero in on the quadratic and logarithmic scoring rules. These feel pretty different intuitively, right? The log scoring rule goes off to -infinity. The quadratic scoring rule does not. And one way to formalize this intuition is to think about how much the expert cares which outcome happens as a function of their report. So concretely, if an expert says 99.99%, and they're being rewarded with the log scoring rule, then they really care which outcome happens, right? They really want the yes outcome to happen. And that's this plot in the bottom right corner. So in a sense, by using the log scoring rule, the elicitor renders a value judgment that probabilities close to 0 and 1 are in some sense extreme. To formalize this, I'm going to define a function capital G. Capital G is the expected reward of a truthful expert as a function of their belief. So in the bottom right corner, I've drawn the functions capital G for the quadratic and log scoring rules in the case of a binary outcome. You might notice that these functions are both convex, and indeed this is always the case. But more important for us will be the derivative of capital G, which we will label lowercase g. So lowercase g represents how the expected reward of a truthful expert changes as a function of their belief. Why do we care about this function little g so much? Well, I want to draw your attention to this chart, which shows the function little g for the quadratic and log scoring rules. You might recall that this is the same chart as the one that I showed you 2 slides ago, when I was discussing how much an expert cares about which outcome happens as a function of their report. That is exactly what the function little g captures. So the key idea of QA pooling is, well, as we discussed, the choice of a scoring rule renders a value judgment about how the expert should think about various probabilities. And it makes sense to render that same judgment when aggregating those probabilities. So the idea of QA pooling is to mediate your averaging of the probabilities through the function little g. I'd like to illustrate what I mean with a couple of examples. So let's say that expert 1 thinks there's a 90% chance of something, and expert 2 thinks there's a 2% chance. First, I will show you how we pool these 2 forecasts with respect to this linear function g, which is precisely the little g corresponding to the quadratic scoring rule. So here's what we're going to do. We'll begin by dropping vertical lines from these 2 forecasts and see where they hit the function little g. We'll take those y values. So one is around -2 and the other is between 1 and 2. And we're going to average them. Then we're going to draw a horizontal line followed by a vertical line to map this point back into probability space. And this new point, which turns out to be 46%, is the QA pool of 90% and 2% with respect to this function little g. So with respect to the quadratic scoring rule. Now we're going to play the same game, but with this new curve g, which is precisely the little g corresponding to the log scoring rule. So again, we're going to drop vertical lines, see what those values are, average them, and map that back to probability space. And in this case, we get 30%. No surprise, we used a different curve. We got a different answer. And in fact, it shouldn't be surprising that this answer is lower. And that's because, remember, the log scoring rule treats probabilities such as 2%, which are close to the 0 and 1, as extreme. And so in a sense, this expert pulls the average closer to them. I will now give you the formal definition of QA pooling. And this should be exactly what you're expecting, given what we did on the previous slide. So here's the definition. Given forecasts P1 through PM and a proper scoring rule S, the QA pool of these forecasts with respect to S is defined as follows. We'll take the little g values of these forecasts and average them. Then we will map that average back to probability space by finding the forecast P with the property that G of P is equal to this average. Now, I want to note that it is really easy to incorporate weights into this definition to get a notion of weighted QA pooling, if you trust some experts more than others. The only change is that instead of taking a straight average of the little g values, you take a weighted average. So as I mentioned earlier, QA pooling maps the quadratic scoring rule to linear pooling and the log scoring rule to logarithmic pooling. So it maps the two most commonly used proper scoring rules to the two most well-known opinion pooling methods. This should pique your interest, and indeed, in the remainder of the talk, I hope to convince you that QA pooling is a pretty natural or maybe even a fundamental notion. I will begin by telling you about two senses in which QA pooling is optimal. The first of these is something that we decided to call max-min optimality. So let's say that you are asked for a forecast and you'll be paid according to the scoring rule S. Now, you happen to not know anything about the subject at hand. And so to come up with your forecast, you decide to subcontract M experts. Maybe you trust these experts different amounts, so you assign them weights, adding up to 1. And you will pay these experts according to the same scoring rule S times their weight. Your goal is to turn a profit. So specifically, you want to maximize your worst case profit over all possible outcomes, J. And when I say profit, what I mean is the score that you get minus how much you need to pay out to the experts. It turns out that the forecast that maximizes this worst case profit is precisely QA pooling. Another way to phrase this result is that QA pooling maximizes the amount by which you can improve over just choosing an expert at random. The second notion with respect to which QA pooling is optimal is through something known as Bregman Divergence. So let me tell you what Bregman Divergence is. Let's say that you have a convex function, which I've suggestively called capital G, and two values x and y. Then the Bregman divergence with respect to G from x to y is defined as follows. And you might want to look at the chart in the bottom right. Draw a line through y tangent to G. And how far below x that line passes, that is the Bregman divergence from x to y with respect to G. Now, given a proper scoring rule, the Bregman divergence from x to y with respect to G, where G is the expected reward function of the scoring rule, is exactly how much you lose out by saying y if the right answer is x. And so a really natural question to ask is, if you have several conflicting reports from experts, P1 through PM, along with weights, what is the single forecast that minimizes the weighted sum of the Bregman divergences to the experts' reports? And the answer, again, is exactly QA pooling. So what this means is that the QA pool is the forecast with the property that the experts are least sad in aggregate if that is the right answer. And so in a sense, the QA pool can be thought of as a compromise between the experts' forecasts. Now, I hope that these two optimality notions have convinced you that QA pooling is pretty interesting. And if so, you might be wondering, well, there is a QA pooling operator for every proper scoring rule. So what does the class of all QA pooling operators look like? And we answer this question with an axiomatization of QA pooling. So specifically, we prove that a pooling operator is a QA pooling operator with respect to some proper scoring rule, if and only if it satisfies a certain list of axioms. And these axioms extend an axiomatization by Kolmogorov and Nagumo of something called quasi-arithmetic means, which is how we got the name quasi-arithmetic pooling. And I won't go through these axioms now, but I am happy to come back to them and answer questions about them after the talk. Now, if these facts about QA pooling have convinced you that QA pooling is pretty natural or maybe even fundamental, then it's natural to ask, where can we go from here? What new vistas does this open up for us? And one possible path for exploration is to think about expert weights. So far, we've been taking expert weights for granted, but where did these weights come from? And how might we learn them? So concretely, let's say that for T time steps, you receive reports from experts, and you want to QA pool them with respect to a particular proper scoring rule S, with weights that you get to choose. And then after every report, you are rewarded with the scoring rule S based on your report and the eventual outcome. Can you learn these weights efficiently? The answer turns out to be yes. In particular, if you use an online convex optimization algorithm, such as online gradient descent, then you can guarantee yourself a reward that is almost as large as if you had used the best possible weight vector for the experts in hindsight. That's a pretty strong no regret guarantee, right? We're not saying no regret with respect to the best expert in hindsight. We're saying no regret with respect to the best possible weighting of experts in hindsight. And this property falls out of a really nice mathematical property of QA pooling, which is that your score is a convex function of the weights that you assign to the experts. I hope that I've convinced you that QA pooling is natural or maybe even fundamental and merits further study. If so, I have some ideas for possible future work. For example, this is closely related to some work on arbitrage from colluding experts. And it might be interesting to flesh out that connection, as well as to look for relevance of QA pooling to Bayesian settings, or perhaps trading-based interpretations of QA pooling. Additionally, it might be interesting to try to extend the no regret result that I told you about to a broader class of proper scoring rules, including possibly unbounded scoring rules under some additional assumptions. That's it, and I'm happy to take any questions. Thanks.